Thank you very much. Thank you very much for the invitation, and it's a great pleasure to be here. So, since it's a number theory conference, I will start with some motivation from number theory. So it's a classical result in analytic number theory that if you compute the density of all the square free integers, over all integers, you get the inverse of zeta 2. There's another result, slightly less well known, but still true, that if you take the density of all pair of integers, n and m, there is relative prime over all pair of integers, you still get zeta 2 inverse. So you see that even though these things look kind of unrelated, but somehow they give you the same number. There's a generalization of both of these results. So more generally, if you compute the density of all m tuple of integers that are relative n prime. So relative n prime, meaning their GCD is n power free. Again, I'm not going to write down. Over all m tuple of integers, you will get zeta and m inverse. So here, there's some sort of, so in particular, you see that the density over here is dependent only on n and m. So even though the set, the density you're computing might look wildly different, but somehow the result is the same. So whenever you see such a coincidence, you may be inclined to ask, what is the function field analog of this thing? And hopefully we see some geometric intuition why this thing should happen. So over function field, so algebraic geometry. So we want to formulate this density as some sort of density between point count on some variety or scheme. So let me start with the convention of, or the algebrogeometric convention that I'm going to use today. So all my schemes are finite type over a field, algebraically closed field. And when my scheme, so when x comes from x naught over k, which is fq, then I'll use the usual notation of x naught fq to denote the set of all fq points on x. And then lastly, I will use the notation lambda to denote the field of coefficients for cohomology. So for example, when all my schemes are defined over some field of characteristics P, then I will take lambda to be QL bar, just with analytic cohomology. So for example, lambda equal to QL bar for étale cohomology. Okay, so now we're done with the convention. So let's go back to formulating this thing, right? So here, kind of the underlying thing is all this zeta are for z, right? So in algebraic geometry, we want to replace that by some scheme. So let x be such a scheme. And then let's come up with the analog for this guy, or more generally this guy. So that's z, again, z. Wait, let me. So let D be an M tuple of integers. I have denote Z, D, N, X, so X is a scheme, to be a sim of D1X times sim of d mx. So that's the analog for the denominator over here. So I would like to think of them as space of colored particle with multiplicities. So that's the thing that takes care of the denominator. So how about the numerator? So we want the numerator to be an open subscheme of here, right, imposed by this extra condition over here. So, here should be infinity. So the reason why it's infinity will be clear in a moment. So dnx will be a open subscheme of zd infinity x. So again, another name for this guy, sometimes people write sim d of x. Such that no point in x has multiplicity of at least n for every color. Right, so let me quickly give an example of what this really means. So let's consider the case where m is equal to 1 and n is equal to 2. Then in this case, m equal to 1 means that there's only one color, meaning that the denominator is just one symmetric power. Right? And n equal to 2 means that no point has multiplicity more than 1. So that means that z d 2 of x is precisely just sim d of x, but remove all diagonals. Right, so you have all these points, but you don't allow any point to collide. Namely, each point has multiplicity at most 1. How about m equal to 2 and n is equal to 1, right? Then z of d, which is now a tuple of numbers, so d1, d2, 2x, is just sim of d1x times sim of d2x, but you want them to be disjoint. Namely, no point in x appear twice, right? So you want square, but you don't want anything to be the same in both factors. Okay, so now what do we mean? Okay, so now what do we want? So there's an analog of this result in the function field case. It's essentially the same as this one, except that the zeta function now will be the zeta function of x, and the dimension of x is going to show up. So again, assuming that everything comes from FQ, so we can compute we can look at the number of points on these schemes. So we look. Any question? So look at ZD N X FQ over ZD infinity X FQ. And we take the limit, and it's known to be zeta of x, evaluated dimension of x, so I will for now denote by d, times m and n. So in particular, it depends only on the scheme x itself and the product m and n. So now as promised, whenever we see such a thing in algebraic geometry, we want to at least guess that this coincidence, the fact that it only depends on m and n, has a homological origin. So guess. The coincidence has homological origin. Right? So whatever that means that somehow in the end we want some kind of complex of vector space that somehow encode the cohomology of this guy and cohomology of this guy, and somehow when we take Frobenius trace, we get this guy. Right? That's kind of the thing that we expect. Okay, so even though we don't know exactly what the homological origin is, at least it should cast some shadow on other phenomena instead of just point count. So here's one way we can make sense of this phenomenon. So again, other guess, suppose that this does indeed come from homological origin, and we guess that. So here, right, in this expression, we have some limit when d goes to infinity, right? So we want to say something like this. We look at the cohomology of this space, right, and so how we take the content of it at infinity and do the same thing for here, and somehow we divide one by the other, we get something that depends only on M and N. Right? That's kind of the guess that we have. Okay, so here I just said that take the content of homology at infinity. What does that even mean, right? So here's what it means. So we want to say that the cohomology of Z, D, and X. Right? So again, taking base chain to arbitrarily closed field and take some sort of cohomology, say analytic cohomology. We expect that there are maps between them, right? Because we can have one categorical level up. So to kind of make sense of limit, we want map between them. So we want map between them, between one level to the next, such that for each degree, rather cohomological degree, right, for each of these dots, the map is an equivalence when D is big enough. Right? We want some sort of stability of this cohomology. Right? So this phenomenon is called homological stability. Okay, now suppose that we do have homological stability, right? So suppose that is true. We can define, say, A, M, N, X to be the stable homology. Right? So we let D go to infinity, and so we get a piece, a stable piece. And then similarly for the case where N is infinity, right? This is for Z, D, N, and this is for Z, D, infinity. Then if we believe that this is a reflection of some homological origin phenomenon, then we expect that, say, if we take the Poincare polynomial of this guy divided by Poincare polynomial of this guy, we should get something also only depend on M and N, or product of M and N. Or if we take, say, the cohomology of all of these guys and take some sort of graded Euler Poincare trace for the Poincare characteristic and divide one by the other, we also get something like that. Right? So we want all sort of things that we would expect if this thing actually comes from some homological origin. Okay, so these are the expectations. So let me write down some progress that kind of been done in answering this question. So one of the first attempts was done by Church and Knudsen. So these are topologists. So they proved that, so always X smooth. They proved that homological stability does happen when in the case of configuration spaces, namely in the case of M is equal to 1 and N is equal to 2. And then other people, so Cooper and Miller, so they also prove homological stability, also for the case X smooth, when M is still equal to 1, but N is anything. And then there's recent work by Ford, Wolfson, and Melanie Wood. So they actually proved that homological stability for all M and N. And also coincidences in densities of Poincare polynomials or Euler characteristics. Right? There are a couple of other things that essentially follow the same theme. So let me quickly give a remark about the method of these people, how they actually prove these things. Okay, so Wolfson and Wood's method. So what they did is that essentially they So they try to get a handle on the cohomology of this guy by using the Leray spectral sequence of the open embedding from this guy to the symmetric power of X, and then use a method from algebraic combinatorics, something called John Vach's theory, to handle the combinatorics of the strata in the complement. So that's what they do. Okay, so now that this has been done, so now what are the remaining questions? All right, so the first question you want to ask is that earlier I wrote the density, right? I didn't say that X has to be smooth. So now the question is, what happens when X is not smooth? How about X non-smooth? So the second question is that, so when you use combinatorics to answer this question, so you do some explicit computation and you see that, oh, the result is the same. It still doesn't quite answer why the coincidence should appear, right? You prove something by explicit computation, so you don't know. So what's really the source of the coincidences here? Right, so in this talk, I will try to answer these questions using factorization homology. Okay, so let me introduce some notations. So I will use the following notation to denote that it's joint union of all of these guys. Right, so I'll put all of these together in one big scheme for OD. And then similarly for infinity guy, which is the same as this guy. Now we also denote A, M, first AD, ADN to be the cohomology of this guy. And then, so this is the chain. And then similarly, so all of these things are cohomology of the corresponding space. Right? So it should be clear what hopefully the notation I'm using is referring to. Okay, so first of all, right, so the source of our question is something about we take something and divide by something else. So when you think about cohomology theory, usually you don't get to divide one thing by the other, right? The only thing you usually do is you have a short exact sequence, and you get a long exact sequence, and then you have all the characteristic, which is an additive invariance. You get like this thing equal to this thing plus this thing, nothing to do with dividing, right? So we have to come up with a way to encode how to divide things, not just how to add things or subtract things. So what is the upshot of the strategy? So kind of the first guess is the following. So suppose you have A and B, commutative algebra, say the graded commutative algebra, right? Equipped with a map from A to B, and say A is augmented, so say everything is over the ring lambda that I'm going to take cohomology using this coefficient. So suppose I have something like that, and I take relatives. I take derived tensor of B, tensor over A by lambda. So all my tensors are derived. So let me not write the L everywhere. So the upshot is that one should think of this thing as the calorification of B divided by A. So let me give a quick example of what I mean by that. So suppose A is equal to lambda t, where degree of t is equal to 1. So a graded commutative algebra where the generator is graded degree 1. And B is just lambda, right? And so I want to, now suppose I want to compute the graded Euler characteristic of A. And the variable that I'm using is U. then I will get what? I will get 1 plus u squared, right? So on and so forth. So that's give me 1 over 1 minus u. Right? And then similarly, if I take the derived tensor, then I will have the following. A lambda, so that if you compute that, then you will get lambda with lambda considered in degree 1, in degree -1. So this corresponds to this guy. And if you compute the graded Euler characteristics, so let me call this here. So this is 1, this minus u. So you see that this is the inverse of this guy, which at least in this case, explain this source of heuristics, right? So we want to kind of bootstrap this source of reasoning to somehow allow us to talk about densities by sort of derived tensor products of algebras. Okay, so now that suggests that what we should do is the following. So first of all, we should equip the homology of all these guys with the structure of a commutative algebra. So we want to equip this guy M and N X, which consists of all the homology of all the configuration spaces. Equip all this guy with commutative algebra structure. Right? And then we also want maps between them, right? So the map is actually coming almost for free, pretty much for free, because we have an open embedding, so that induces a map on the cohomology level by pulling back. Right, and then we want to prove that the tensor AMN x over AM infinity x lambda, again derived, depends only on x and m and the product mn. Right? That's the categorical thing that we want to prove. And moreover, once we've done that, we can also make sense of the homological stability, namely, note that H0 of AMN. So this is taking connected components, and I start with connected schemes. So this thing is going to become lambda with T1, Tm, right? So Ti has cohomological degree or 0. So that means that this guy acts on this guy by multiplying by these Ti's, and that move to the next level, right? If I multiply by Tm, right, then that means that, so for example, Tk, right, will allow us to multiply by Tk, will allow us to move from D to A, D plus 1 at degree K, and X. So it allows us to at least make sense of what we mean by homological stability. So now we have an explicit map. The job is now to show that this satisfies homological stability. Right? Okay, great. So now this is what we want. So how do we get there? So that's what factorization homology is supposed to help us. So let me move to the second part. So factorization homology has its roots in physics and in vertex operator algebras, and was formulated in the world of algebraic geometry by Berlin and Trimfeld. And it has a lot of use in geometric Langlands and also recent proof of the Tamagawa #1 conjecture of a function fields by Gaisgri and Lurie. So kind of the salient feature of factorization homology that we're going to use is that it's multiplicative. So I'll explain what it means precisely pretty soon. And the second feature is that there's a trace formula in the style of Grothendieck-Lefschetz trace formula, but now it's the result, one side has Euler expansion. So Euler product. Which is a good sign, because in the end we want some kind of zeta function, right? So this is a good sign. Okay, so let me say exactly what I mean by multiplicativity. Okay, so now, given a scheme X as before, I will use the notation sheaf X to denote the derived categories of analytic sheaves on X. And the monoid, so usually when people do tensor between sheaves, they use the usual tensor. The tensor I'm going to use is the strict tensor. So you box tensor them on the square and pull back using the exceptional pullback. Right? So just to remind you, so if I have F and G, then I do this. This is by definition is F exceptional tensor with G. Right? Okay, so now I have a category and a monoidal structure, so I can look at the category of commutative algebra objects in that category. Right? So consider commutative algebra objects on sheaf of X by using this thing. So namely, an object in here is equipped with maps that looks like this. Right? These are my multiplication maps. Right? So that's what I mean by, and satisfy commutativity and so on in a certain suitable sense. And again, because I'm working with these objects, right, that are naturally graded, so it's useful to keep track of the grading. So what I really want is Z to the M graded algebra objects. Right? So most of this talk, I will kind of ignore the grading to make it light on the notation, but the idea is essentially the same. Okay, so now again, I want to emphasize that the version of factorization homology that I'm using is a much simplified version that suffices for our application. So it will look simpler than what you would see. So I denote pi to be just the structure map of X. And so I have the following. So first, a commutative algebra object in vector space, right? As a commutative algebra object in sheaf in X with respect to this strict tensor product, I can pull back, because pull back preserve this monoidal structure. So that means that if I start with something commutative here, commutative algebra here, then I still get something commutative algebra here. Right? But the push forward, unfortunately, doesn't preserve the monoidal structure. So that means that if you just do the naive push forward with compact support, you won't land in here. However, this functor commute with limit. So some abstract nonsense tells you that there exists a left adjoint to this functor. So it's just abstractly there's something that gives you a commutative algebra in vect given a commutative algebra in sheaf on X. Right? So for now, it's just abstract. But at least this cannot give you a hope, right? Because this somehow gives you something commutative algebra in here, which is what we're looking for. Right? Okay, so what is the when something is defined abstractly, it's a bit scary because we don't know what it's actually doing, right? So one formal fact is that, so being a left adjoint, it preserves free objects. Namely, if you apply pi lower question mark to a polynomial algebra in here, then you will also get a polynomial algebra. So namely, sim V, right? So polynomial algebra generated by some sheaf V, and that's the same as sim of pi lower strict of V. Right? So at least it's something that is not too bad. Right? So somehow, for free stuff, it just does the usual thing on the generators and then take the sim after that. So it's not too bad. All right. Okay, so now you may ask, what does this have anything to do with configuration spaces, right? So I started with configuration spaces. These spaces look somewhat complicated. And here all of a sudden I move to the sheaf on X and there's no configuration spaces. So you may wonder how I recover back the thing that I wanted. Right? In other words, what should I plug in here, right? So that when I apply pi lower question mark, I get the homology of these spaces that I was studying before. So what links to these A, M, N, X, or just to recall, this is homology of Z, M, N, X. Okay, so even though the functor pi lower question mark is defined by abstract means, there's somewhat concrete way to compute them using these spaces. So so this construction is called the delta lower question construction. So what does it do? So again, everything here should be graded, but let me ignore that fact. And essentially, the idea is the same. So what does it do? So suppose I start with the commutative algebra object in the category of sheaves on X. Right? The goal, we want to attach to it. So again, so delta really is to denote this diagonal map to all these guys. The Z, M, Z, D, and X. So again, I'm ignoring the grading. There should be some D there, but let's pretend there's one map. Okay, so the goal is that I want to produce a sheaf on this guy. Right, so in fact, infinity. Right, so to somehow link the algebra here to this guy over here. Okay, so now, what is the construction? So the construction is very simple. So let me give you what happened in X squared. Right, so let's see what happens. So essentially, you have the following. So you have the multiplication map. So you have X squared here, and this is the complement U, and this is the standard divisage sequence. Right. So first I have the multiplication map. Right, so I have this guy here, I push it here, and this guy, I take the tensor product, and I do this. And then there's also a natural map, like so, by just adjunction, and I push out. I get a sheaf on X squared. Right, so here you see that the sheaf A, this sheaf has the special property that when you restrict to U, then you will see that it's just essentially box square of A restricted to U. Right? So that's where the name factorization comes from, but we don't actually use much of that. All we really need to know is that there's construction like this, right? So for higher power of X, there's a more complicated diagram that you compute the push out or the co-limit, but essentially it follows the same idea, using the multiplication map to somehow glue one copy of A on the diagonal X, and the box time tensor of A on the complement, to somehow glue them together using the multiplication map. So that's the idea. Okay, so now I do have a sheaf, right? So what now? So the result is that, so it's due to Bellinson and Drinfeld and Gates-Gray and Lurie, is that the cohomology of the resulting sheaf on this space compute this functor. Right? So pi lower question mark of A is the same as cohomology of this guy with value in this guy. Right? So that's great. It's a good news that we link together something defined abstractly to these spaces, which is what we want. Right? Okay, so now the next question is, now what A I should plug in to recover the cohomology of all these guys. Right? So which A do we want? So it turns out to be surprisingly simple. So let's start with the simplest case. So it's a straight A. So first, let's deal with the case where M infinity, right? So we just have the free algebras. Okay, so suppose we take the factorization homology of X with value in this commutative algebra, right? This is a free commutative algebra. Then what I said earlier, I said that you just compute the usual guy and take the sim. And then by Q-net theorem, we know that that's precisely the cohomology of, so by Q-net, we know this is precisely the cohomology of Z M infinity X, which is my curly n infinity x. Right, so this part is easy. Right? So now the next part is how about the other guys? So someone can prove the following. So again, these xi has some homological degree and also some tail twist, but let me ignore that. Essentially, just twist so that it lands in the right place. So for the other guy, AMN is just lambda x1 to xm divided by x1 multiplied with m all to degree n. And the claim is that pi low question mark of AMN is the same as a cohomology of Z MNX. Right, so at least intuitively, right, why is it true? So essentially what you're doing here, right, you make stuff to be 0 after a certain degree, right? And when you look at this formula, essentially when you do this, and when you glue and when the multiplication map is 0, then you essentially kind of erase the strata that you're removing from the cohomology. That's kind of the intuitive content of this result. Okay, so now we know a way to capture the cohomology of these spaces using factorization homology. So now let's return to the first question we asked. What is the thing that captures the coincidence in densities? So now it's actually very clear. So namely, when you compute the following push out, so again, because this guy, pi low question mark, is a left adjoint, so it preserves push out. So in particular, to study these densities, right, it suffices to study densities in using just these polynomial algebras, which is a much simpler question because there's no x involved. Right? So we want to compute the following push out, AMN to lambda. Right? So just another name for derived tensor product. So this guy is the polynomial algebra cut out by one equation. So the tensor product is simple to compute. So namely, it's just this. Okay, so here I want to say that there's a small lie here. Because essentially these things don't live in degree 0. So really here there's some other shifting that should be replaced, but just slightly more complicated number. But essentially the computation is still the same. It's still defined by one equation, so it still look like that. Right? So in particular, this number here will only depend. So actually, let me just be honest and write it down. But it looks somewhat more convincing. So the actual result that you get, so again, these things should have appropriate shifting. So what you really get is lambda shifted to degree 1 minus 2dmn, and then tail twist by minus dmn. Right, so that's the actual number when you put the appropriate shifting here and here. So here you see immediately that that the result depends only on m and n, right off the bat. And second, the zeta mn that you saw earlier when you compute the product, and when you apply the trace formula to this case, the multiplicative trace formula, you will see that the dmn is the thing that is responsible for the zeta dmn that appear in the beginning. So that's how the two are linked together. Okay, so now that we know that using factorization homology, we can link the cohomology of these spaces to factorization homology. But one thing remains, namely, we just know abstractly that there is a device that allows you to recover the cohomology, but we don't know how to have a handle of it yet. We don't know how to compute anything. We just know that there is abstract isomorphism between these two guys. So the next thing that allows us to actually get a handle on this cohomology is something called Koszul duality. So the version, so again, Koszul duality is some device that was invented by Quillen to study rational homotopy theory. And the version that I'm using here is Koszul duality between commutative algebra and Lie algebra. So essentially it says that there's pair of functors, namely start with the Lie algebra, you can form the homological Chevrolet complex, namely the thing that computes Lie cohomology to get a commutative algebra. And then for commutative algebra, you can get a Lie algebra by something called the derived tensor, derived tangent fiber. So essentially, some sort of derived version of tangent. So this is actually augmented, to be augmented. So fiber, the tangent at the point given to you by the augmentation. And then in nice cases, namely, actually in the cases that we are considering, these two functors are equivalence of categories. So how does it help us? So essentially, if we let A, Mn, and A, M infinity to be the Lie algebra correspond to this commutative algebra, A and A M infinity, then the following statement is true. So this is due to Francis and Gates-Gray. The statement is that if you compute pi low question mark of A, M, N, then it's the same as applying the Lie cohomology functor to pi lower strict of A, M, N. And similarly for the case where N is equal to infinity. So this is kind of the generalization of the free polynomial, the polynomial algebra case, that this is kind of more general. Okay, so now still look a bit abstract, but actually now we are pretty close. So the first thing we need to do is to compute what these Lie algebra are, right? So AM infinity is actually simple, so it's just generators of A M infinity, right? So it's just a m-dimensional vector space, so with correct homological and degree grading, and AMN is essentially generator and relation for AMN. Right? So what do I mean by general relation? So essentially, it has the same guy as the this thing, right? But also has one term that corresponds to the relation. So this guy is where the relation happened. So just so you have the flavor of what this thing looks like. So essentially, it's very simple. Right? So now the question is, okay, so now we have a handle of these guys. And now the question is, what kind of information we should extract from this cohomological Chevrolet complex to actually prove what we want. So what does Koszul give us? Right, so the first thing is that even though it's abstractly defined, it has very nice formal properties. So the first property is that, in fact, the only property that we actually use is that Koszul has a filtration whose associated graded is just sim. Right, so essentially, we use this to reduce to the case where the thing in question is just have trivial Lie structure. And so using this, we can prove many things. So for example, homological stability is easy to prove for a symmetric algebra. Essentially, just look at where the generators are and what monomials you can get at each cohomological degree and graded degree, and then you are done. And then using the same thing, essentially it says that if the categorification is additive, right? Namely, for example, Euler characteristic, then the cat of Chevrolet or something is multiplicative. Right? Namely, we actually make sense of the heuristic that I said at the beginning. And so using these things, the final result is that we can prove, so let me just give kind of the gist of what it's saying. So we can prove homological stability for cohomology of these guys. And then see a source of, we actually have a conceptual understanding of where the coincidence comes from. And finally, by which once we decategorify the thing, right? We recover the densities in like point count or Euler characteristic, and so on. Right, so that's time is up. So that's it. Thank you.
Questions, comments?
Yes.
You mentioned just now that this factorization homology has a Euler product as
Yes.
expression, but you didn't really.
Yes, I can write it down, yeah. So essentially the shape looks like this. So up to some finiteness, to make sure that the infinite product that you write actually makes sense, it has the following shape. So suppose you have A is a sheaf, commutative algebra, sheaf on X, right? Then it has the following shape, so pi A, so trace of Frobenius is the same as the product, X over all closed point of X, and then trace of Frobenius at X inverse to the co-stock of A. So that's kind of the shape that it has. So that's the Euler expansion. You get product of all closed points.
So we know there's next speaker again.
Thank you.